Plane Trigonometry Chapter 8, Section 1, Angles, Arcs, and their Measures. First, we have some basic terms, and these are going to sound very familiar from geometry. Two distinct points A and B determine the line AB. The portion of the line, including the points AB, is the line segment AB, and the portion of the line that starts at A and continues through B is called ray AB. An angle is formed by rotating a ray, called the initial side, around its endpoint, which is called the vertex, to a terminal side, and you see that illustrated there. Okay, a little bit more about angles. An angle can have a positive or a negative measure. Now, this is different from geometry. Geometry, our angles were always positive. In trigonometry, they can be positive or negative. An angle that is created when the terminal side rotates counterclockwise from the initial side is a positive angle. And an angle that is created when the terminal side rotates clockwise from the initial side is a negative angle. So you see one angle drawn here, and the one on the left would be a positive angle because the curve, the arrow there, is indicating that it starts in the initial with the initial side and it opens up in a counterclockwise manner. The one on the right is a negative angle because from the initial side, CB opens in a clockwise manner, so it is negative. An angle may be named using the vertex, so we could call these angles, both of them really, angle C, or you can use a point on each ray and the vertex and put the vertex in the middle. So we could call these angles ACB or BCA. Now notice that for both angles, they're named the same. It's really important when you draw an angle that you illustrate which direction it is opening using a curved arrow like the one you see here in red. How it's determined is they divide the circumference of a circle into 360 parts. This goes all the way back to the Babylonians who developed their calendar and all sorts of things. If you're wondering why 360, it just goes back to their base of counting. They used a base 60 system. We use base 10. So it seems a little odd to use 360, but that's where it came from. There are 360 degrees in one rotation. In other words, you go around the circle once, that's 360 degrees. 1 degree is 1 over 360 of a rotation. It's 1/360th of a rotation. An acute angle is an angle between 0 and 90 degrees. A right angle is an angle that is exactly 90 degrees, which means it's 90 over 360 or 1/4 of a rotation. An obtuse angle is greater than 90 but less than 180. And a straight angle is exactly 180. In other words, it's 180 over 360 or half of a rotation. So halfway around the circle is 180 degrees. The sum of two positive angles is 90, then those angles are called complementary. And if they add up to 180, they're called supplementary. So we're going to try an example here. You want to find the measure of each angle in the given figure. Okay, use the fact that two angles that add up to 90 are complementary. The other two add up to 180. Do a little bit of algebra here. Try the problem, pause the recording, give it a try, and resume to check your answer. All right, for part A, we just want to say that 6m plus 3m equals 90, and then solve for n, and we get m, and we get 10. Putting that back into the two angles, 6 times 10 is 60, 3 times 10 is 30, so our angles are 60 and 30. For B, we're going to set those equal to 180. We're going to add 4k plus 6k and say that equals 180, which means k is 18. Putting those back into the two expressions, we get that the angles are 72 degrees and 108 degrees. Now, angles can be expressed in degrees as decimals, or they can be expressed in a system called degrees, minutes, seconds. 1 minute, which is written as 1 with an apostrophe, is 1/60th of a degree. So, in other words, 1 minute is 1 degree over 60, or 60 minutes equals 1 degree. 1 second is written as a 1 with, it looks like quotation next to it, and that is 1/60th of a minute. So 1 second is 1/60th of a minute, or 1/3600th of a degree. Or another way of putting it is that 60 seconds equals 1 minute, which kind of makes sense. So we're going to perform the calculation: 51 degrees, 29 minutes, plus 32 degrees, 46 minutes. Pause the recording, give this a try, and resume to check your answer. Okay, just add them together and you get 83 degrees and 75 minutes. But 75 minutes, 75 is 60 plus 15. In other words, it's 1 degree plus 15. So it's going to be 84 degrees, 15 minutes. Now we're going to convert between the degree, minute, seconds and the decimals. And we're going to do this two ways. So we're going to try these. You got to remember that a minute is a 60th. So you take the minutes over 60, and then you're going to take the seconds over 3,600. Give this a try. We've actually done this before. See if you can do it. Pause the recording and then resume to see how you did. So for part A, what we're going to do is we're going to do 74 plus 8 over 60, that's the minutes, plus 14 over 3,600, that's the seconds. And you just add all those together and you get about 74.137. B is a little trickier. What you do is you separate it into 34 plus 0.817. And then what you're going to do is you're going to multiply the 0.817 times 60 for the minutes. That gives you 49.02. And then you're going to separate that into 49 minutes plus 0.02 minutes and multiply the 0.02 by 60 for the seconds. So we get 34 degrees, 49 minutes, 1.2 seconds. And do this using your calculator. So after all that, I'm going to give you the shortcut. To convert degrees, minutes, seconds to a decimal, you enter the number followed by the appropriate symbol as shown. I'll show you that in a second. The degree and minute symbols are in the angle menu, and the seconds symbol is alpha plus. So hit the alpha key and then plus. And then to convert a decimal to degrees, minutes, seconds, you enter the decimal. This one's even easier. Enter the decimal and then go again to the angle menu, which is second apps, and choose the fourth item, which looks like a triangle with DMS. So here you see two pictures. One is the angle menu, and again, you get that by hitting the second button and then the apps. And you'll notice that to convert the degrees, minutes, seconds, you need the symbols. And the very first item on the menu is the degree symbol. And the second item is the minute symbol. Now the second symbol is not in this menu. It's actually on the face of your calculator. And to get it, you hit alpha plus. To go the other way, it's even easier. Like I said, if you look down the angle menu at number 4, you have a triangle and DMS. That stands for degree, minutes, seconds. You simply put the decimal in and then choose that item on the menu. And you can see there in the screenshot that you get it in degree, minutes, seconds. So very easy way to convert between the two types of systems. Now, an angle is in standard position if its vertex is at the origin and the initial side is along the positive x-axis. An angle is in standard position is said to lie in the quadrant in which the terminal side lies. So for example, you have an angle here. It's in standard position. Notice the initial side goes from 0, 0 to the right along the x-axis. The vertex is at 0, 0. And when it opens, the terminal side is in quadrant 1. So we would say that this angle lies in quadrant 1. This angle, on the other hand, would be said to lie in quadrant 2. Even though it spans across 1 and 2, you call it by where the terminal side stops, and it stops in quadrant 2, so this angle is said to be in quadrant 2. And then this is just to give you an idea. Angles between 0 and 90 will be in quadrant 1. Between 90 and 180 will be in quadrant 2. 180 and 270 will be in quadrant 3, and 270 to 360 will be in quadrant 4. And notice that the 0, 90, 180, 270, 360, those are not actually included as part of the quadrant. We'll talk about those in just a second. Now, those angles are called quadrantal angles, and they are angles that in standard position have terminal sides along the x or y axis. So again, we're talking 0, 90, 180, and 270. They're not considered to be a part of any quadrant. Instead, they are called quadrantal. And they rest on the axes. Now, coterminal angles are angles that have the same initial side and the same terminal side. For example, we see a picture here. We have a 60-degree angle, which is just the basic, go from the initial side to the terminal side, nothing fancy. And then you'll notice we have another angle that's marked 420 degrees. We get this by rotating the initial side all the way around the circle and then back 60 more degrees. 360 plus 60 is 420. Because these two angles have the same starting place and the same stopping place, they are considered coterminal angles. By the way, you could also have negative coterminal angles. So the 60-degree angle there, if we had shown the rotation as going clockwise, we would have a negative 300-degree angle, and that would be coterminal with the 60-degree angle. Now, it's really easy to find these because the angle measures differ by a multiple of 360. In other words, to find coterminal angles, add or subtract multiples of 360 to the given angle measure. So for our 60-degree angle, add 360, you get 420. Add 360 to that, you get 780. Those are all coterminal angles. You can also subtract. 360 or 60 minus 360 is going to be negative 300. Minus 360 is negative 660. So those would all be coterminal angles. And you see in the second illustration here, we have a 110-degree angle. If we add 360 to that twice, we get 830. Those are coterminal. And again, you can subtract also to get coterminal angles. Try this. Find the angles of the smallest possible positive measure that are coterminal with these two angles. Pause the recording, give it a try, and resume to check your answer. Okay, so we're going to add or subtract 360 as many times as needed to get an angle between 0 and 360, because that'll be the smallest positive. So 908, we are going to subtract 2 times 360, which is 188. And for B, we're going to add 360 to negative 75 and get 285. So 188 for the first one and 285 for the second. It says let n be an integer. We have an infinite number of coterminal angles. For example, 60 degrees plus n times 360. What this is saying is that there is no limit to the number of coterminal angles that you can find. You can get ridiculously large or ridiculously small, because all you have to do is keep adding and subtracting multiples of 360. Now let's talk a little bit about radian measure. An angle with its vertex at the center of a circle that intercepts an arc on the circle in length equal in length to the radius of the circle has a measure of 1 radian. Okay, so if you look at the picture there, we've got a circle in blue, and then we have an angle opening up in red, and that angle is designated by the Greek letter theta. That's what that symbol is. It's very common to use theta to represent angles. It's very common as you get into higher math to use Greek letters to represent angles. So we'll use theta a lot. And R represents the radius of the circle. And what it's showing us there is that the arc length, the curve, the length of the curve, if you were to measure it, would be the same as the length of the radius. And when that happens, the angle that's created has a measurement of 1 radian. The radian is a real number where the degree is a unit of measurement. Radians relate the arc length and the radius. They relate things together. They're easier to use that way. Degrees don't really relate the angle and the arc length. You have to do a lot of computation to make that work. The circumference of a circle, which is c equals 2 pi r, where r is the radius, shows that an angle of 360 has a measure of 2 pi radians. So 360 equals 2 pi radians, which means 180 equals pi radians. So in other words, once around the circle is 360 degrees, it's also 2 pi radians. Now there's a couple ways you can convert between degrees and radians. One is 2 steps. You multiply a degree by pi over 180, and that converts it. Or if you're trying to go from a radian to degree, you multiply the radian by 180 over pi, and that will convert. And this is a good way to go. Another way to go, and this is the way that we've looked at before in Algebra 2 and Algebra 3, you can actually set up a proportion Radian over degree equals pi over 180. Notice that the radian and the pi are both on the same level of the fraction. They're both here in the numerator, and the degree and the 180 are on the same level. Here they're in the denominator. You can actually flip both of these upside down and it will still work. So you could do degree over radian equals 180 over pi. And then what you do is you fill in what you have and you solve for what you're missing. So if they give you the radians, you fill that in and you solve for the degrees. If you're given the degree, you fill that in and you solve for the radians. So these are two ways that you can use to convert between degrees and radians. So let's see, 1 radian is equivalent to about 57.3 degrees. If an angle measurement is being given in degrees, then you're going to see the symbol for degrees following the measurement. But if you don't see a symbol, then it's understood that the angle is in radians. So if you're wondering, look at the number. If it has a degree, it's degrees. If it doesn't, it's radians. All right, so convert 249.8 degrees to radians. Pause the recording, give this a try, and resume to check your answer. Okay, so we're multiplying 249.8 times pi over 180. You can use whichever method you want to solve for this, and you should get approximately 4.360 radians. Now try converting 4.25 radians to degrees. Pause the recording, give it a try, and resume to check your answer. And we get 243.5 degrees. Okay, now we're going to do this, but we're going to use our graphing calculator. And what I'm going to do is just kind of walk you through this instead of asking you to do it, because obviously you've not done it this way before. So we're going to do the same problem we just did. We're going to convert 249.8 degrees to radians. And how we're going to do that is you're going to put your calculator in radian mode. And if you're wondering how to do that, you're going to hit mode, and then you're going to go down. You'll see two items next to each other. One will say degree, one will say radians. You're going to switch it to radian. So put it in radian mode, and then go back to the home screen. And what you're going to do is you're going to put 249.8, and then you've got to put the degree symbol in there. And when you do that and hit enter, it will convert it to radians. So you can see here what happens. If you want to pause and give it a try on your calculator, make sure you've got how to do that. You need to put the calculator in radian mode first, enter the measure followed by the degree sign, and then hit enter, and it gives you the answer. Now we're going to do the same thing, but the other way around. We're going to convert radians to degrees. So what we're going to do here, again, it's very similar. We're going to put the calculator in degree mode, and then we're going to enter the measure followed by the radian sign. Now, if you're wondering where that is, again, go to the angle menu, which is second apps, and it is, I think, the third item on the menu. It's a little R, so you're going to put that there. So we'll put 4.25 R, hit enter, and you get 243.5. And if you check to what we got previously, they should be a match. This is just a chart of some equivalent angle measures in degrees and radians. You notice we've got it for 0. Now 0 is real easy because it's 0 across the board. 0 degrees, 0 radians. Don't worry about the approximate. I mean, you can get those easily on your calculator, but you are going to want to be very familiar with the exact. So 30 degrees is pi over 6. That's a good thing to get in your head. 45 is pi over 4. For me, that one's kind of easy because it's got the 4 in it, so it just kind of links really naturally. The 60 degrees is pi over 3. 30 and 60 can be easy to confuse because the 30 is pi over 6 and the 60 is pi over 3. So if you kind of remember that it's kind of an opposite thing there with those numbers, it might help. 90 is pi over 2, 180 is pi, 270 is 3 pi over 2, and then 360 is 2 pi. You're going to see these a lot, and you're going to want to have the exact values, the pi, with the pi involved, instead of the decimals most of the time. So you really need to get these equivalents down in your head. Now, there's a couple of formulas that we can use since we now know how to use radians. The length S of the arc intercepted on a circle of radius r by a central angle of measure theta radians is given by the product of the radius and the radian measure of the angle, or S equals r theta, where theta is in radians. Now you'll notice here that I put radian in bold print every single time, and there's a reason for that. We've done this before. You do this in Algebra 2. We do this in Algebra 3. The problem is, it's a very simple formula, but people forget that the angle must be in terms of radians. And it will give you the angle in terms of degrees sometimes. And you have got to make that conversion before you use the formula. So you really need to get it in your head that the angle has to be in radians in order to use this formula. So try this example. A circle has a radius of 18.2 centimeters. Find the length of an arc intercepted by a central angle of 144 degrees. Pause the recording, give this a try, and resume to check your answer. All right, so notice the first thing we do right out of the box is we change 144 degrees to radians, and you see the process there. Then we can put it into the formula. Generally with arc length, we are going to go for a decimal equivalent here because it is a length, and it makes more sense for lengths to be expressed in terms of a decimal. We also have the formula for sector area. In the area of a sector, by the way, the sector would be if you think about a circle, think about cutting it into slices like a pizza. A sector would be one slice of the pizza. That's all it is. The area of a sector of a circle of radius r and central angle theta is given by area equals 1/2 r squared theta. And again, notice theta in radians. You'll notice in the bottom here in red, I made a note. Notice that as with the arc length formula, the angle must be in radians. If it is given in degrees, you must convert the angle to radian measure first. I know I keep pounding this and it's a little redundant, but honestly, when we've done this in the past, this has been the major mistake that people make on these formulas. They're not difficult formulas, but we forget to convert our angle to radians, and it's very important that you get that in your head. Okay, so we have a little problem here. The figure shows a field in the shape of the sector of a circle. Find the area. So you have the radius and you have the angle measure. Pause the recording, give this a try, and resume to check your answer. First, we convert the degrees to radians, which gives us pi over 12, and then we use the formula 1/2 radius squared times theta. So it's 1/2 times 321 squared times pi over 12, and that gives us about 13,500 meters, square meters. And a couple more formulas that we're going to deal with are angular speed and linear speed. Angular speed is symbolized by the Greek letter omega, looks kind of like a W, and it measures the speed of rotation. And it's defined by W equals theta over t. Theta is the angle measure in radians, and t is the time. Linear speed, which is symbolized by kind of a fancy V there, is defined by velocity. Linear speed equals s over t. S is the linear distance, and t is the time again. Since the distance traveled along a circle is given by the arc length s, we can rewrite velocity or linear speed as s over t. S would be r theta, there's our arc length formula, over t, and then they kind of factored out the r. So r times theta over t, well, theta over t is the angular speed. So what they're saying is that the linear speed of something going around a circle is the radius times the angular speed. Now, if you're wondering what's the difference between angular speed and linear speed, angular speed is how fast that angle is turning. Things like revolutions per minute would be an angular speed, or degrees per second would be an angular speed. Linear distance would be as if you took a tape measure and you measured, if you could just straighten out the circle, straighten out the curve, how far in a straight line did that point, that person, that whatever travel. That would be, or how fast in a straight line would it be. That would be your linear speed. Linear distance would be how far it traveled. This is a little application problem. We have a belt that runs a pulley of radius 6 centimeters at 80 revolutions per minute, and you have a little picture there. Find the angular speed of the pulley in radians per second, and then find the linear speed of the belt in centimeters per second. Pause the recording, give this a try, and resume to check your answer. Okay, so in 1 minute, the pulley makes 80 revolutions, and a revolution is 2 pi radians. So 80 times 2 pi means it's going 160 pi radians per minute. Now that is the angular speed in radians per minute. but what they wanted was radians per second. So what we need to do is we need to figure out how many seconds are in a minute, which hopefully you know that's 60, and we're going to divide 160 pi by 60. So that gives us 8 pi over 3 radians per second for our angular speed. The linear speed will be the same as that of a point rotating on the circumference of the pulley. So we're just going to use our formula. It's going to be radius times the angular speed. The radius was 6, and the angular speed was 8 pi over 3, which gives us 16 pi, or about 50 centimeters per second. Okay, here's another example. A satellite traveling in a circular orbit 1,600 kilometers above the surface of the Earth takes 2 hours to complete an orbit. The radius of the Earth is 6,400 kilometers. Find the linear speed of the satellite and find the distance traveled in 4.5 hours. Pause the recording, give this a try, and then resume to check your answer. So the distance from the Earth's center is 8,000 to the satellite is 8,000 kilometers. One orbit is 2 pi, so the distance is r theta, which is 8,000 times 2 pi. So within 2 hours, we have 8,000 times 2 pi over 2, which is 25,000 kilometers per hour. Our distance is velocity times time, so 8,000 pi times 4.5, and we get 110,000 kilometers. This is just some additional practice, so if you will pause the recording as you go through these and give them a try, and then resume to check your answer. Proceed this way through the rest of the recording.